All right. Hello, class. Hope everyone had a wonderful Labor Day weekend. So let's talk about some things that we went over in class last time. So I do have to apologize. I kind of got ahead of myself and I put down the wrong definition for what it means to have a row reduced echelon form. So last week's definition is wrong. So I'm sorry. I just need to apologize about that. I kind of got ahead of myself. What I meant to write down last time was that was our goal. The definition that I had down for row reduced echelon last week was supposed to be the goal of, like, if we want to look for one solution only. And we'll talk about those things later on in this lecture. But before we get to those things and kind of correcting that definition we have, let's talk about a few definitions and go over some examples real quick. And then we can begin to get to the meat of this lecture. This lecture is mostly going to be going over row reduced echelon form, what it means to have a matrix in row reduced echelon form, how to interpret solutions to a linear system when we have a matrix in row reduced echelon form, and then just going over and doing row operations to get a matrix in row reduced echelon form like we did last class. So just some more practice with that. But first, we just have to go over again what it means to have a matrix in row reduced echelon form, because again, last week, the definition I had down for what it meant to have row reduced echelon form matrices was the wrong definition. So let's just clarify some things and let's go over some new definitions first. So the first definition we have here is what it means to have a leading entry in a matrix. Well, or I should say the leading entry for a row in a matrix, because leading entries are things that rows have. So notice here that it's called the leading entry for that row. So rows have leading entries and matrices have rows. So for example here, I'm going to put down a quick example. We've got the matrix, 1, 0, 2, 3, 2, 0, and then 0, 1, 1. Our leading entries for this matrix is going to be the 1 here, the 3 here, and then the 1 here. So the leading entry, we have the leading entry for row 1. I'm going to put leading entries, and then row 1, the leading entry for row 1 is going to be 1. The leading entry for row 2 is going to be 3. Then the leading entry for row 3 is going to be 1. Notice that it's the first non-zero entry in that row. So we're looking at the entire row. So notice, this entire row here, this entire row here, this entire row here. But if I look at it, the leading entry for this first row is here. And again, for the second row is here, but the leading entry for the third row is in the middle column, because that first entry for the third row is 0. So leading entries are the first non-zero entry in each row. That's just, if you hear me say leading entry, that's what I mean when I say leading entry. Again, another quick example here, I'll use a different color. So let's say we have a matrix like this, 1, 0, or actually I'm going to say 0, 1, 2, 0, 0, 2, 1, 3, and then 0, 3, 1, 2, 2. Here, if I do, again, trying to find my leading entries, let's see, I'm going to write down, let's see if you can guess what it is in your head real quick. So what is leading entry for row 1 and row 2? I'll give you like 5 seconds to kind of figure it out. So again, we want to look at the first row. We want to look at the rows. So my first row, I only have 2 rows here, my first row and my second row. And I want to notice what's the leading entry for the first row. Well, I've got 2 zeros and then a 2. My first non-zero entry is 2. And then what's my leading entry for row 2 is going to be 3. I've got 1, 0, and then a 3. So it's just the first non-zero entry. And I'm just circling where the leading entries are. You can have a leading entry in a row that's further down. So here all my leading entries were in column 1 of my, or I should say my leading entries in row 1 and row 2 were in column 1. But here my leading entries are, further down. So you can have a leading entry anywhere. And it could be that a row doesn't have a leading entry. And I guess I'll draw that example down here. So sometimes, let's say, I've got this matrix 0, 0, 0, 0, 0, 1, 2, 2, and then 1, 0, 0, 2. So my leading entry, I don't have a leading entry for row 1. And I'm going to make that not go as far out. So there's no leading entry for row 1 in this matrix here. Now we say the column for our second definition, definition 2, a column of a matrix is clear. So now we have a property that we're assigning to rows. Or first definition 1, we have a property that we're assigning to rows. And now I've got a definition that I'm assigning to columns of a matrix. So a column of a matrix is clear when it contains only one non-zero entry. So let's look at what that means. So if I take my example, from here, so if I take this matrix, I copy it, I'm going to paste it down here, and I'm going to get rid of some things. I'm going to get rid of all the highlights because I want to highlight different things and bring different things to your attention. So if we look at this, we're going to look at the columns now. Look at the columns. None of these rows are clear because if I look at it, none of these columns are clear because if I look at it, I've got a 0 here, but these two entries are both non-zero. And I need exactly one non-zero entry. And again, here I have a 0, so that's nice. And then here I have a 0. But in these columns, I still have more non-zero entries. So this matrix has no clear columns. I'm going to move that to the side a little bit. Now, if I take this matrix here, I'm going to copy it and paste it down here. I'm going to erase some things. And we're going to look at the columns again. If I look at all these columns, there's only one clear column. Can you guess which one that is? It's going to be this one. Now, you might think, well, what about, column 1? Well, that's not clear because every entry is 0. I need to have only one non-zero entry. So there needs to be at least one entry that's non-zero. I can't have all of them to be 0. So here I've got 1, 3, and then 0 everywhere else, and then none of these other rows are clear. And then I'm going to copy and paste this last matrix here. And I'm going to paste it over here. Now, if I look at it, I've got almost every single column is clear. Because here, this column's clear, that checks out because if I look at it, I've got, I'm going to do a different color because it's the same color. If I look at it, this one's clear, that's good because I've got 0, 0, I've only got one non-zero entry, and it's right there. Again, I've got one non-zero entry here, so that's clear, and one non-zero entry here, and that's clear. But this one is not clear, this last one, because I've got two non-zero entries in this one. So I hope this is kind of making sense, and you can kind of see, what it means for a column to be clear, what it means to have a leading entry for a row. And the reason we're bringing these definitions up now is because we want to talk about what it means, really, the true definition for row-reduced echelon form. So a matrix is said to be in row-reduced echelon form, sometimes written just RREF, when it satisfies the following three properties. R1, the leading entry of each row is 1. R2, the columns containing the leading entries are clear. So we talked about already what it means to have a leading entry and what it means for the columns to be clear. So we need the leading entry for each row to be 1. It can't be anything else, it has to be 1. And the columns for every single leading entry needs to be clear. So that means if I look at the leading entry, if I look at the rows, right? If I look at the rows, then that leading entry for that row, when I find the first entry of that row, it needs to be a 1. And then if I look at that row, if I take the column that leading entry is in that row, that column needs to be clear. And then we have the last property that row-reduced echelon forms you to have. The leading entry of each row needs to be to the right of the leading entry in the row above it. And any rows which contain all zeros are at the bottom of the matrix. So this seems like a lot, but we're going to go through quite a few examples, not a few examples, quite many examples, to kind of get the idea of what it means for something to be in row-reduced echelon form. Because when we're solving for systems of linear equations, and we're using our Gauss-Jordan elimination, we're row-reducing our matrices, we want to get them in row-reduced echelon form. So let's look at some examples. I've got quite a list of examples here. So this matrix is in row-reduced echelon form. Because if I look at it, the leading entries for each row is a 1. And then if I look at the columns of this matrix, every other entry in my columns are 0. So that's good. This is row-reduced echelon form. I don't really care about this last column here. And the reason is because the reason I don't care as much about this last column is because, I don't have any more space to have leading entries, right? I've only got 3 possible rows, so I don't have any more rows to go over to the right. Also, at the same time, each of the leading entries are down and to the right of each other, and that's kind of what that R3 is mentioning. So I guess if I'm going to go back, and I'm saying RREF, but let's say I got to check, so let's check each of the properties. R1, is each leading entry 1? So I look at the first row. Yeah, that's 1. The leading entry, right? The leading entry of this one is 1. The leading entry of this one is 1. So yeah, R1 is met. And then I've got I want to check R2. Are the columns clear? And that's what I was highlighting earlier. All right, column 1 is clear. That's good. Column 2 is clear. Column 3 is clear. Whoops. So R2 is met. And I don't need to, again, like I said, I don't need to check for this last column here. And the reason is because I don't have any space to go over to have more leading entries. And then for the last one, we've got R3. Is R3 met? Are all of my leading entries down and to the left? Is if I look at a leading entry, if I start at the bottom, typically you start at the bottom, sometimes you can start at the top. So if I look at this leading entry, is the leading entry above it to the left of it? And the answer is yes. It's to the left. And then is the leading entry above this leading entry to the left? The answer is yes. So we want our leading entries. If I have a leading entry above in a row above one leading entry, it needs to be to the left of it. So let's look at example 4. Let's go through it again. R1, are my leading entries 1? Yep, that one's 1. For row 2, it's 1. And then for row 3, I don't have any leading entries. So this means yes, all my leading entries are 1. Now let's check R2. Are my columns clear? And you might be thinking no, but that would be wrong because I only need to check the columns of my leading entries, where my leading entries are in. So I have a leading entry in row 1, column 1. I only need to check column 1 then. That's good. And this, because this is not a leading entry, 3 is not a, sorry about my handwriting, leading entry. Because 3 is not a leading entry, I do not have to check column 2. But I do need to check column 3 because 1 is leading entry and it is clear. So my R2 is met. And then for the last one, R3, are my, I'm going to start here. Does this leading entry, if there's a leading entry above it, is it to the left? And the answer is yes. It is to the left. I'm going to the left. So R3 is met. So then overall, yes, this is RREF. And this one is also in row reduced echelon form. Example 5. If I look at example 5, however, can you see, I'm going to tell you this is, example 5 is not in row reduced echelon form. And I'm going to see which one of these does it break. Does it break R1? Does it break R2? Or does it break R3? It's got to break one of those 3 in order for it not to be row reduced echelon form. So let's look at it. I have a leading entry who's 1, leading entry here is 1, leading entry here is 1. So it seems like R1 it meets. Now let's check R2. If I check R2, okay, I've got non-zero here, I've got non-zero here. However, for the second row, I've got a non-zero here, but if I look at this top entry, this is not non-zero, so it breaks R2. So I don't even need to check R3. R3 doesn't matter. It doesn't meet R2. The columns are not all clear. So we're going to say column 2 is not clear. So it's not in row reduced echelon form. And again, example 6, let's look at it. Does it break, R1, R2, or R3? Which one does it break? So let's go through it. Are my leading entries 1? Okay, I've got a leading entry here. That's 1. A leading entry in row 2. I don't have any leading entries in row 3. So all my leading entries are 1. It meets R1. Let's see, are my columns clear? So I got to check column 1 and column 2, or I'm sorry, column 1 and column 3, because those are where my leading entries are. And it does meet R2. All right, good. However, does it meet R3? And if I look at it, in row 2, I've got a leading entry, and in row 1, I've got a leading entry. But for the row above row 2, row 1 has a leading entry to the right of the leading entry in row 2, which means that R3 is not met. So this is not row reduced echelon form. Now I'm actually going to type it with red up here so you know which one we broke. Not row reduced echelon form. And that's because because leading entry in row 1 is right of leading entry in row 2. Now, I think our last example here, let's look at it, is this row reduced echelon form. And let's check it. So first we got, 3 rules, 3 propositions, properties to check. R1, R2, and R3. So let's look at it. Does it meet R1? Okay, I have a leading entry here, and I have a leading entry here, and they're both 1, so it meets R1. Good. Now, for each column that I have leading entry, are my columns clear? All right, this column's clear. However, if I look at this column here, this column is not clear, so doesn't meet column 3 is not clear. I have a leading entry in row 2. My leading entry in row 2 is in column 3, but column 3 is not clear. So this is not row reduced echelon form. All right. I hope that these examples will be good enough for you guys to understand what it means for something to be in row reduced echelon form. I know that I kind of messed up last time, but I hope that you can kind of look at these, and I'll post some exercises with solutions on the Moodle page for you to look at, and you can kind of try it out. Okay, are these in row reduced echelon form? Because it's important for us to know when something is in row reduced echelon form. And we need, because that's going to be our goal. Our goal is going to be to row reduce our matrices to be in this row reduced echelon form, so we can solve and interpret the row reduced echelon form and what it means for our system of linear equations. Now, let's continue what we were doing last time. I took these from the previous notes, so we never got to the last 2 examples, so I copied them and I pasted them in these notes, so you don't need to go back to the old notes to look at them. Actually, I probably, the only thing that's really useful in those previous notes are the row operations, the definitions of the row operations, which are correct, but the definition of what it means for something to be in row reduced echelon form is not correct, so I'm sorry. I know we're kind of working backwards here, but it's important for us to know what it means for something to be in row reduced echelon form, and that's why it's important for us to spend time on this, and I apologize, for the last lecture kind of making a blunder there, but this is the correct definition of row reduced echelon form right here. So I'm going to give you some practice problems with some solutions on the Moodle page if you want to continue kind of practicing what it means for something to be in row reduced echelon form on your own, so you kind of know what the goal is. And last week I kind of typed in what the goal was, but not what the actual definition was, which is yeah. So let's go back to row reducing. So we know what the goal is. The goal here is to get, well, first, I should say, step 1, find the augmented matrix. And then step 2 is our goal, do row operations to get our augmented matrix in row reduced echelon form. That's our goal. This is what we want to do. So the augmented matrix so we've got 3 systems of linear equations, and we've got 3 unknowns with 1, column of solutions. So I'm going to have a 3x4 augmented matrix. So I'm going to put that in. All right. So I've got my 3x4, so I'm going to have, remember, the entries of the augmented matrix are the coefficients next to my variables in my system of linear equations. So I go look at the first I look at the first equation. I've got 1, 1, 1, 1. The second one's got 2, and then -1 because of that minus sign here. And then 1, and then 0, and then 4, 1, 3, 3. This is my augmented matrix. Some people like to put the bar here, if that makes you feel better. So now I'm going to write out what the row operations are going to be. So I've already got, remember, we want to get in row reduced echelon form. So I want my leading entries all to be 1. So I've already got a leading entry here, which is 1. So I don't need to do anything there. And I want this column to be clear. So I want a clear column, which means that I want these two entries to be 0. So because I want to clear this column, I want to clear column 1 now. In order to do that, because I've already got a 1 there, it makes it pretty easy. So I'm going to take negative row 1, add it to row 2 to get new row 2. And then I'm going to take negative 4, I'm sorry, this should be a negative 2 row 1. Negative 4 row 1, add it to row 3, and then get new row 3. And this is going to get me my new augmented matrix. So my first row remains unchanged because I didn't do anything to it. The second one is going to change. I'm going to get a 0 here because negative 2 plus 2 is going to be 0. Now negative 2 times 1 is negative 2, then plus negative 1, that's going to get me negative 3 here. And then I'm going to get negative 2 plus 1, that's going to be negative 1. And then negative 2 plus 0 is going to get me negative 2. And then again, from row 3, I'm going to get 0 because I'm multiplying that 1 by negative 4. And then I'm going to add negative 4 to 1, which is negative 3. Add negative 4 to 3, which is negative 1. And then add negative 4 to 3, which again is negative 1. And this is going to be my next, after I do my row operations, this is going to be my reduced matrix. And I'm going to keep reducing my matrix because I want to get row reduced echelon form. So now, as you can see, I've got zeros here. My columns are clear. I've got my first leading entry is 1. That's good. And then the rest of my columns, the rest of my entries in my column is 0. So I'm on the right track here. Now my next step is to get a 1. I want to get a 1 as the leading entry because I have a leading entry here. This is my next leading entry, but I want the leading entry to be 1. I want the leading entry in row 2 to be 1. So what I'm going to do is I'm going to multiply row 2 by negative 1/3. So negative 1/3 row 2 gets me new row 2. And that's going to get me, my row 1 and row 3 remained unchanged. So 1, 1, 1, 1. But here I'm going to have 0, and then this is going to be 1, multiplied by negative 1/3. But this is going to be 1/3, and this is going to be 2/3. And then here, this is 0, negative 3, negative 1, negative 1. All right. This is my new augmented matrix. So this is good because now my leading entry here is also 1. My leading entry here is 1, but I want to have my columns, I want this to be cleared. I want my column 2 now to be cleared. I cleared column 1, and I've got a leading entry 1, that's good, in row 1. Now I've got a leading entry of 1 in row 2, but I want this second column now to be clear. So I'm going to clear column 2. And the way I'm going to do that is by taking negative row 2. Sorry if you can't read my handwriting. Negative row 2. Really trying here. And then adding it to row 1 to get new row 1. And then I'm going to do 3 row 2 and then add it to row 3 to get new row 3. So row 1 remains the same. 1, 1. Actually, no, it doesn't. I've got row 2 remains the same. So 0, 1, 1/3, 2/3. Now, row 1, I've got 1 here. Now I've got 0 here. But negative 1/3 plus 1 is going to get me negative 2/3. Then negative 2/3 plus 1 is going to get me negative 1/3. And then here, I've got 0 here, and I've got 0 here as well. But I'm multiplying 1/3 by 3, which is going to get me 1. And when I add that to negative 1, I get 0. And then 2/3 times 3 is going to get me 2, and I add that to negative 1, that's going to get me 1. All right. Now, I don't have a leading entry now. Actually, I do have leading entry. I've got leading entry here, and now I've got a leading entry here. Now that I just happened to get a leading entry here on accident. I wasn't trying to, but I did, and that's okay. But now, since I've got a leading entry there, I want to clear column 4. And the way I'm going to do that is I don't have to write down here now. I'm going to do 1/3 row 3 plus row 1 gets me new row 1. And then I'm going to do negative 2/3 row 3 plus row 2 gets me new row 2. And here's what that's going to get me. My bottom row stay the same, 0, 0, 0, 1. But here, my first row is going to be 1, 0, negative 2/3, 0. And then my second row is going to be 0, 1, 1/3, 0. Now, in terms of my original system of linear equations, so remember, this first column represents, so we'll first recognize that this is now in row reduced echelon form. I've got my leading entries. I've got my leading entries are all 1. The columns of my leading entries are all clear. And my leading entries are, up and to the left of each other. So if I have a leading entry in the row above one of my leading entries, that leading entry is to the left. This is good. This matrix is now in row reduced echelon form. Row reduced echelon form. Oh my goodness. Sorry about that. All right, row reduced echelon form. Excellent. However, this poses a problem in terms of my original equation, because let me paste it down here, and let's recall what it means, for my augmented matrix, right? So this is my augmented matrix. There were 0, this is 0. So this is my augmented matrix, remember that. So that means that all these columns represent something. So this column represents the value for x1, this column represents the value for x2, this column represents the value for x3, but this column represents the value for, this is equal to, whatever over here. This bar represents the equal sign. This is what my equations are equal to. But if I translate this matrix back into a system of linear equations, I get x1 minus 2/3 x3 is equal to 0, which isn't a huge problem. And then I get x2 plus 1/3 x3 is equal to 0. That's also not a huge problem. What's a huge problem is I get 0 which is equal to 0x1 plus 0x2. I'm going to say, I'll start out here, 0x1, right, because I've got a 0 here, plus 0x2, I've got a 0 here, plus 0x3, I've got a 0 here, is equal to 1. In other words, oh, wow. Oh, excuse me, I'm sorry about that. That voice crack is uncanny. Oh, I don't have a water next to me, another huge blunder. Anyways, what this means is I've got 0 equals 1. But we all know that that's impossible. You can't have 0 equal to 1. That breaks all our rules of math. So what happens here is when we get a augmented matrix in row-reduced echelon form, and I've got something like this bottom row here, where for all the columns, I'll say for all my columns, I've got zeros for all my columns that represent my variables, right? Because the first column represents my x1 unknown, the second column represents my x2 unknown, the third column represents my x3 unknown, and this last column just represents, the other side of the equal sign. If all my x1, x2, x3 columns, if all the columns for my unknowns that represent my unknown variables are 0, but I have a non-zero value on the other side of my equal sign. That's why people like to draw the bar here to remember that that represents the equal sign. If I have all zeros for all of my columns except for the last column in any one of my rows, that means I'm going to have no solution. Because again, it's impossible. This is not a correct statement. This statement right here, this statement is a false statement. It's false. Right? 0 is not equal to 1. It's just not possible. Which means that I've got no solution for this system of linear equations. That's what this row-reduced echelon form represents. When I have something in row-reduced echelon form like this, and I've got a 1, but all the other entries, again, it's really important that we recognize this, that all the other entries for all my other columns are 0. And this final entry is a 1 right here. It's important to understand what that means and interpret that. That's when I have no solution. Now we're going to look at something else. Another type of example. So let's turn this into an augmented matrix. So I've got 1. Well, first let me just do the highlighting. For some of you, it might be easier to see it that way. So I've got 1, 2, 3 equations. And I've got 1, whoops, kind of 1. I've got 1, 2, kind of trying to involve that 2, then 3 unknowns, and then the other side of my equal sign. So I'm going to have 3 rows and 4 columns again, and in my first row I'm going to have 1, 1, 1, 1, and then 1/4, -1/2, and that's supposed to be, I believe, oh no, I think that's a plus right there. So 3/4. Got the plus, and then 0 on this side, and then 1, 7, -3, 3, and this is my augmented matrix with the, can you guys see that color? No, probably not. Let's see, I'm going to do this color. This is lavender color. This is the other side of my augmented matrix, the other side of the equal sign. That bar represents kind of my equal sign here. Now let's row reduce. We notice here I've already got a leading entry of 1. That's excellent. So I want to clear column 1 now. I'm going to do that. I'm going to add, multiply -1/4, row 1. Actually, no. Let's get rid of the fractions first, actually. Just to make our life simpler, right? So let's actually multiply everything by 4 in row 2. So 4 row 2 gets me new row 2. Let's do that first. Just get rid of all those fractions. This is a common technique. If I don't like seeing those fractions, right, I can multiply them all by the common denominator that they all could have. So I've got 4 and 2. Since 4 is a multiple of 2, I'm going to multiply everything by 4. So 1, 1, 1, 1. Then I'm going to get 1, negative 2, 3, 0. And then 1, 7, negative 3, 3. And that's going to be my reduced matrix after multiplying everything by 4 there. And now I recognize, now I can clear, I am so sorry for my handwriting. Clear column 1. That's our goal. Because notice again, I've got a leading entry of 1 for my first row. So let's clear column 1 now. I'm going to do negative row 1 plus row 2 gets me new row 2. And then negative row 1 plus row 3 gets me new row 3. Awesome. So let's do that. I get 1, 1, 1, 1. And then 0, negative 3, 2, negative 1. And then 0, let's see, negative 1 plus 7, I don't know why I blanked there, 6, negative 4, 2. That's going to be my reduced matrix. And then now I have, this is a leading entry, and the rest of my entries are cleared, are 0. So my first column is clear. That's good. My next goal, I want to get a leading entry of 1 here. Whoops. So let's get a leading entry of 1 here by, multiplying by negative 1/3. Row 2 gets me new row 2. And so that's going to get me this reduced matrix 1, 1, 1, 1, 0, 1, and then let's see, negative 2/3, 1/3, then 0, 6, negative 4, 2. Great. Now I've got a leading entry of 1 here. That's good. Let's go ahead and clear column 2. Let's clear column 2. I'm going to take negative row 2, and then I'm going to add it to row 1 to get new row 1. Then I'm going to take negative 6 row 2, then add it to row 3 to get new row 3. So here I've got 0, 1, negative 2/3, 1/3 for my second row. But here I'm going to have 1, and then this is going to be 0. But then negative 2/3, positive 2/3, I add that to 1, I'm going to get 5/3. And then I've got negative 1/3 plus 1, that's going to get me 2/3. And then here I've got 0. Here is also going to be 0. Negative 6 times negative 2/3 is going to be 4, positive 4. So this actually turns out to be 0. And then I've got negative 6 times 1/3 is going to be negative 2, and this turns out to be 0. So just by a, happy coincidence, I guess you could say, I'm done. Because I've got a leading entry of 1 here, and I've got a leading entry of 1 here. And then my row 1 is clear, my row 2 is clear. All my rows with my leading entries, column 1 is clear, column 2 is clear. All the columns that contain my leading entries are clear. I don't have to worry about these last 2 columns because they don't contain leading entries. I don't have any more leading entries. It's not possible for me to because the rest of my entries for row 3 is 0. I don't have a leading entry for row 3. What does this mean though? Well, this means, remember that, I'm going to move this down I'm going to copy and paste. And I might even shrink it just a little bit to make it easier to work with. So remember that the columns, again, what do the columns represent? They represent our unknowns. And this side of the column represents my equal sign. So here, this is x1, x2, x3, and then this is what, this column represents what they're equal to when I add them together. So if I convert this back to an equation, a system of linear equations, I just get x1 plus 5/3 x3 is equal to 2/3. And then I get x2 minus 2/3 x3 is equal to 1/3. And then because this bottom is completely zeros, so this is where there's a difference. This final entry is not non-zero, it's 0. And here, I'm going to write this out, even though you don't have to in the future, 0x1 plus 0x2 plus 0x3 does equal 0. This is a true statement. It is true. So what this implies is that I actually have, if I'm going to continue and I'm going to write this out as a solution, my solution explicitly my explicit solution here is going to be x1 is equal to 2/3 minus 5/3 x3. Then x2 is equal to 1/3 plus 2/3 x3. So I've got values for x1 and x2, and then x3 we say is a free variable, or in other words, can be any number I want it to be. What does this imply? This implies that there are infinitely many solutions. So again, remember that earlier we had three different types of solutions, right? For our system of linear equations and two unknowns. We could have exactly one solution. We could have no solution or infinitely many solutions. And we see that here being reflected in our row-reduced echelon form. Whenever I have a matrix that looks like this, whenever I have a matrix that looks like this here, right? This is going to be no solution because I have 0, 0, 0, 1. I have 0x1 plus 0x2 plus 0x3 is equal to 1, which doesn't make sense. That's no solution. But down here, I've got 0x1 plus 0x2 plus 0x3 is equal to 0. And that's okay. That's a true statement, which means I can write my other two variables as a system that's dependent on x3, which means that I can choose any number I want for x3 and get a solution for x1 and x2, and that solution satisfies my original system of linear equations. Which means that there are infinitely many solutions because there are infinitely many values I can choose to plug in for x3 and get another value for x1 and x2. So that's exactly what we want. So there are times when we have no solution. There are times when we have infinitely many solution. It just depends on what type of row-reduced echelon form matrix I have. So this is in row-reduced echelon form, this matrix here, and we kind of have to interpret what the row-reduced echelon form matrix means in context. So we're going to do a couple more examples. I think I'm running on 49 minutes. All right, I think we can do these last couple of examples. So let's turn this into an augmented system of an augmented matrix. So notice here, though, that this is x1, x2, x3. So in my matrix, I'm going to have 1, 1, 5. But then since there's an x4, I'm going to put a 0 there and then a 1. Then this one begins with x2, so I have 0 for x1, 1 for x2, 2 for x3, 1 for x4, and then 1. This one has all my variables, so 1, 1, 5, 1, and then 1. Then 1, 2, 7, 2, 2. So this is my system of linear equations. Now I've got a leading entry of 1 here, so all I have to do is take, I guess we're celebrating someone today. Sorry, you can probably hear them in the background, but I hope it's not too much of a distraction. Anyways, we do have a leading entry there. It's 1. So now I'm going to get rid of, we want to clear column 1. Let's clear it. So negative row 1 plus row 3 is equal to, I get new row 3. And then negative row 1 plus row 4 gets me new row 4. So let's see what that new matrix now looks like. I'm going to get, I have to write this a little bit smaller. 1, actually I'm going to make all of this smaller. Let's make it smaller. All right, yeah, that's a lot better. So let's go back. We've got our first row remains unchanged, 1, 1, 5, 0, 1. The second row we didn't need to, it's already got a 0, so 1, 2, 1, 1. The second row remains unchanged. Now the third row is going to be 0, and then it's going to be 0, and then 0, and then 1, and then 0. And then our fourth row is going to be 0, and then 1, and then 2, and then 2, and then 1. So this is going to be our reduced matrix. Now, let's see, I've got this column is now clear. We're good. Next, I want to focus here. All right, in row 2, I've got a leading entry of 1. Now, since I've already got a leading entry of 1, I don't need to, do anything. Let's clear column 2. So in order to clear column 2, I'm going to take negative row 2, add it to row 1 to get new row 1. And then I'm going to take negative row 2, add it to row 4, and get new row 4. I'm so sorry about my handwriting. Let me see if I can fix that. Row 4. I'm kind of writing at an awkward angle here. All right. Now, row 2 remains unchanged. So 0, 1, 2, 1, 1. And then row 3 remains unchanged because it's already got a 0. So there we go. And then, so I've got 1 here. This is going to be 0. Negative 2 plus 5 is going to be 3. Negative 1 plus 0 is going to be negative 1. Negative 1 plus 1 is going to be 0. And then for row 4, I get 0 here, another 0 here. Negative 2 plus 2 is 0. Negative 1 plus 2 is 1. And then negative 1 plus 1 is 0. So I get this. And then there might be something that you notice here. So this column's good, this column's good. Now my next leading entry is here. And I want to clear, you can probably already see what's going to happen because the last two rows are the same, but I'm still going to continue anyways. We're going to clear column 4. We're going to clear column 4 now. So to clear column 4, I'm going to do negative row 3 plus, just regular row 3 plus row 1, new row 1. Then I'm going to do negative row 3 plus row 2 is new row 2. Then I'm going to do negative row 3 plus row 4 is new row 4. Now, what's going to happen here is row 1 is going to be like this. I'm going to get 1, 0, 3, 0, 0. Column 2 remains, well, not remains the same. I got 0, 1, 2, 0, 1. It's not a 6, that's a 0. And then I get 0, 0, 0, 1, 0, then 0, 0, 0, 0, 0. This is my matrix. I forgot to include my bar. Let me go back and add those just for simplicity and consistency. All right, here we go. Now, notice that this row is clear. This column's clear. This column 2 is clear, and then column 4 is clear. That's good. But notice what I have on the bottom here. All zeros. And remember, what did we say when we had all zeros? This looks familiar to our previous one. Whenever I have all zeros, well, that's going to get me infinitely many solutions. With the explicit solution, being this, I have, remember, this is going to represent x1, x2, column 3 is x3, column 4 is x4, and this is my equals. So the explicit solution is going to be x1 plus 3x3 is equal to 0. I'm going to get x2 plus 2x3 is equal to 1. And then I'm going to get x4 just equals 0. But notice that these two equations have x3 in common. So x3 we say, because we don't have anything for x3, x3 is my free variable. Which means I can plug in anything I want for x3. x4 is always going to be equal to 0, but I can plug in anything I want for x3, get a value for x1 and x2, and I've got infinitely many choices for x3. So again, that tells us that we have infinitely many solutions. And this is our explicit solution here. And what I mean by explicit solution is, on a exam, I'm going to accept, if you just want to write infinitely many solutions, I'm not going to expect you to say that x3 is free and say that. I just want you to recognize when you're going to have infinitely many solutions and when you're going to have no solutions and when you're going to have exactly one solution. So let's do one more. We have one more example and then we're going to call it a day here. So let's get our augmented matrix. Again, we have 1, 2, 3 rows, or I should say again, but this time we have 1, 2, 3 rows, and then I've got 1, 2, 3, 4 columns. So let's write down this augmented matrix here. I've got 1, 2, 4, 5. I've got 2, 4, 5, 4, and then 4, 5, 4, 2. This is my augmented matrix with my boom, my little bar, I guess, if you want. So we've got our leading entry is 1, so that's good. Now let's clear column 1. Let's clear column 1 now. And I'm going to do that by multiplying row 1 by -2, -2 row 1, plus row 2 gets me new row 2. And then -4 row 1 plus row 3 gets me new row 3. And my new matrix, my row 1 stays the same, 1, 2, 4, 5. But here I'm going to have 0. But -2 times -2 times 2 is going to be -4. This is going to get me 0. And then 4 times -2, -8. That's going to get me -3. And then 5 times -2 is -10, plus 4 is -6. And then for my row 3, this is 0. 2 times -4 is -8, -3 here. And then 4 times -4, -16. That's going to get me -12. And then 5 times -4, -20, plus 2, that's going to get me -18. So this now is going to be my reduced matrix. And if I look at it, I'm going to use purple this time. If I look at it, here we've got our row, our column 1 is cleared. That's good. But if you notice here, my leading entry for row 2 is further to the right than my leading entry for row 3. We don't want that. We want We don't want that. So let's switch row 2 with row 3 in our matrix. Because we don't want our leading entries in the in the row below to be to the left. We want our leading entries in the row below us to be to the right. So I'm going to switch those rows. 0, -3, -12, -18, and then 0, 0, -3, -6. All right. That's good. Now we do have our leading entries that are down and to the right of each other. So now our goal is to clear, well, first we need to get a leading entry of 1. So I'm going to multiply row 2 by -1/3. -1/3 row 2 to new row 2. So that way I can get a leading entry of 1. So 1, 2, 4, 5. And then 0, 1, 4, 6. And then 0, 0, -3, -6. Awesome. Now that I've got a leading entry of 1, I want to clear, I'm so sorry about my handwriting, clear column 2. Now that I got a leading entry of 1, I want to clear column 2. I've already got a 0 here, so I only need to get this to be 0. So I'm going to say -2, row 2, plus row 1 gets me new row 1. So I've got 1, 0, -4, and then -7. And then this is going to be 0, 1, 4, 6, and then 0, 0, -3, -6. Now this is beginning to look good. I'm getting close to row reduced echelon form, and this column's clear, this column's cleared. The next thing I want to do is get a leading entry of 1 here. So I'm going to do -1/3 row 3 gets me new row 3. And if I do that, I'm going to get 1, 0, -4, -7, 0, 1, 4, 6, and then 0, 0, 1, 2. Now I've got leading entries which are all 1. The last thing I need to do is clear column 3. I want to clear column 3. That's my next step. So in order to do that, I'm going to take 4 row 3, add it to row 1 to get new row 1. And then I'm going to take -4 row 3, add it to row 2 to get new row 2. When I do that, I get 1, 0, 0, and then 1, because 2 times 4 is 8, 8 plus -7 is 1. I get 0, 1, and then 0, but then -8 plus 6 is going to get me -2. And then my last one remains unchanged, 0, 0, 1, 2. And then this is now in row reduced echelon form. I've got cleared columns and leading entries which are all 1. So I'm done here. And remember that this represents x1, x2, x3. This is what they're equal to. Since I've got 1s all across the board and 0s everywhere else, here's I have exactly 1 solution. Now, this is what I was trying to mention last time. So I apologize that I kind of got ahead of myself and got things jumbled up and definitions confused. This is row reduced echelon form. But when I have a row reduced echelon form where the left-hand side kind of looks like the identity matrix, because I've got ones across the diagonal and zeros everywhere else, this is when I have exactly one solution. Because this represents x1 is equal to 1, x2 equals -2, and then x3 is equal to 2. Now, you can write it like this, or you can write it like this. You can say that the solution, it's got exactly one solution, and the solution is 1, -2, 2. Either way is correct. Either way is correct. And I'm not going to take points off if you choose to write one way or the other, but this one up here is just a little bit more explicit, and this one's a little bit more implied because, x1, we always write our solutions in increasing order of what the variables equal. But that's the lecture for today. Just reviewing row reduced echelon form and practicing more row operations and understanding the different types of solutions. We've got 3 different types of solution. You can have exactly one solution to a system. You can have no solution to a system, or you can have infinitely many solutions to a system. And so you're going to need to know the difference. You're going to need to know how to get something in row reduced echelon form, when something is in row reduced echelon form, and how many types of solutions you can have. And you're going to need to be able to take a system. So here's kind of the goal of how to solve a system. How to solve a system. So you need to do step 1. You're going to get the augmented matrix. I'm going to get the augmented matrix, and then step 2, you're going to row reduce to row reduce echelon form, and then step 3 is interpret the row reduce echelon form of the augmented matrix. So that means, what type of solution is it? So infinitely many, only one, or no solution. And if it has exactly one, what's the solution? If exactly one solution, what is the solution? All right. And that's kind of the steps we're taking here. That's kind of the goal that we have, and we're going to try and reach. And next week, we're going to look at problems in context. So we're going to take everything we've learned about matrices and row reducing and systems of linear equations, and we're going to use that knowledge that we now have, this new knowledge, and apply it to real-world problems. So I'll see you next week.